Soviet radar operators tracking the translunar injection burn on July 16, 1969, could calculate the Apollo 11 spacecraft's velocity and trajectory within acceptable margins of error. What they could not understand was how a computer with only 4,096 bytes of memory was controlling that trajectory with precision their ground-based mainframes struggled to match. The anomaly wasn't just technological, it was philosophical. For 2 decades, Soviet computer science had emphasized theoretical mathematics and raw processing power, building room-sized machines that consumed enough electricity to power small towns. The idea that American engineers had compressed guidance, navigation, and life support control into 69 pounds of hardware operating on less memory than a modern microwave oven contradicted every assumption about the relationship between computational power and mission complexity. Within 6 hours of translunar injection, analysis sections at both the Ministry of General Machine Building and the Institute of Applied Mathematics received the same preliminary data. The numbers were being reviewed again because the initial calculations suggested an error in signal interpretation. They were not errors. The Apollo guidance computer was performing orbital mechanics calculations, thruster-firing sequences, and real-time navigation updates, using a fraction of the computational resources Soviet planners believed were minimum requirements for lunar missions. The psychological impact on Soviet technical personnel who understood what they were observing went beyond professional rivalry. It represented a fundamental challenge to their understanding of how complex systems should be built. Soviet computer development had followed a path of centralization and scale, with the BSM series of mainframes representing the pinnacle of their computational achievement. The BSM-6, introduced in 1967, was a remarkable machine by any standard, capable of 1 million operations per second, and supported by teams of mathematicians who had pioneered theoretical computer science. But it filled entire rooms, required dedicated cooling systems, and consumed 23 kilowatts of power. The notion that mission-critical spaceflight operations could be handled by a computer small enough to fit in a spacecraft, operated by astronauts rather than trained computer specialists, seemed to violate basic principles of computational architecture. What Soviet analysts initially interpreted as American propaganda, they would spend the next 2 years trying to reverse engineer and replicate. The confidence Soviet scientists held in their computational approach wasn't baseless arrogance. Soviet mathematicians had made genuine breakthroughs in theoretical computer science, cybernetics, and systems analysis throughout the 1950s and early 1960s. Alexei Lyapunov's work on algorithmic theory, Andrei Kolmogorov's contributions to information theory, and the pioneering cybernetics research at the Institute of Control Sciences represented world-class theoretical achievement. The Soviet Union had also demonstrated early leadership in space automation with the Luna 9 soft landing in 1966 and the Zond circumlunar missions, proving that uncrewed spacecraft could execute complex mission profiles using ground-based control and pre-programmed sequences. This track record created a reasonable assumption that American claims about onboard computational control were either exaggerated or represented an unnecessarily risky approach compared to ground-based guidance with human oversight. Soviet mission architecture for lunar attempts reflected this philosophy, with the L-3 lunar landing complex designed around minimal onboard automation and maximum reliance on cosmonauts manually controlling descent and ascent using optical targeting and hand controls. The spacecraft was designed for pilots, not computers. This approach made sense within the constraints Soviet engineers faced. The Soviet electronics industry lagged significantly behind American capabilities in miniaturization, integrated circuit production, and radiation-hardened component manufacturing. Throughout the 1960s, Soviet factories struggled to produce transistors and early integrated circuits with the reliability and performance characteristics American manufacturers achieved. Through mass production for both military and commercial markets, Sergei Khrushchev, son of former Premier Nikita Khrushchev and himself a spacecraft control systems engineer, would later acknowledge that Soviet electronics represented the critical bottleneck in space technology development. While Soviet rocket engines, metallurgy, and propulsion systems often matched or exceeded American capabilities, the supporting electronics, guidance systems, and computational hardware consistently underperformed. This wasn't due to lack of talented engineers or theoretical understanding. The Soviet economic system simply could not generate the broad industrial base required for advanced electronics manufacturing. American companies like Fairchild Semiconductor and Texas Instruments were producing millions of integrated circuits annually for military aerospace and commercial applications by the mid-1960s, creating economies of scale and competitive innovation pressure that drove rapid advancement. Soviet electronics production remained concentrated in specialized state facilities that prioritized strategic military systems, leaving spacecraft designers with limited options and long lead times for custom components. The Apollo guidance computer emerged from a different industrial and philosophical framework entirely. When the Massachusetts Institute of Technology Instrumentation Laboratory received the contract for Apollo guidance and navigation in August of 1961, the digital computer industry was still in its infancy. Mainframe computers required dedicated facilities, trained operators, and could execute only one program at a time in batch processing mode. The idea of a real-time interactive computer that astronauts could operate directly while performing other mission tasks represented a conceptual leap that required rethinking fundamental assumptions about computer architecture. Charles Stark Draper, the legendary engineer who founded the Instrumentation Laboratory, understood that Apollo demanded not just miniaturization but a complete reconceptualization of how computers and humans should interact during high-stakes operations. Draper had spent 2 decades developing inertial guidance systems for aircraft and missiles, work that taught him computers needed to operate continuously in harsh environments without human intervention for maintenance or adjustment. His vision for Apollo combined inertial measurement with optical navigation and real-time computational control, creating a system where the computer served as both autopilot and decision support tool for the crew. The technical specifications that emerged from this vision seemed impossibly constrained. The entire Apollo guidance computer, including the inertial measurement unit, had to fit within 1 cubic foot of spacecraft volume and weigh less than 70 pounds. It needed to operate reliably in the vacuum of space, withstand the vibration of launch and rocket burns, and function continuously for missions lasting up to 2 weeks without maintenance or reset. Most critically, it had to be absolutely reliable because computer failure during lunar descent or trans-Earth injection meant certain death for the crew. These requirements forced the MIT engineering team, led by Eldon Hall, to make radical choices in computer architecture and component selection. They chose a relatively slow clock speed of just over 1 MHz, prioritizing reliability over raw processing speed. They implemented a revolutionary core rope memory system for permanent program storage, where software instructions were physically woven into copper wires threaded through magnetic cores. This made the program literally unchangeable once manufactured, but also made it immune to radiation-induced bit flips and required zero power to maintain. The erasable memory, used for navigation data and temporary calculations, totaled just 2,048 words, where each word was 16 bits. That 4,096 bytes of RAM had to hold the current mission state, navigation data, targeting parameters, and all temporary variables for every running program. Margaret Hamilton understood these constraints better than almost anyone. Hired by the Instrumentation Laboratory in 1963, she led the software engineering team that would write every line of code the Apollo guidance computer would execute. At the time, software engineering didn't exist as a formal discipline, and Hamilton would later be credited with coining the term to describe the rigorous, systematic approach she believed software development required. She approached programming with an engineer's mindset, treating software not as a support function but as a critical system component that needed the same level of testing, documentation, and quality control as any mechanical or electrical system. This philosophy was revolutionary in an era when many engineers viewed programming as a clerical task, something to be handled after the real engineering work was complete. Hamilton insisted on comprehensive testing, formal verification of critical algorithms, and extensive simulation of failure modes. Her team developed the concept of priority scheduling, where the computer could interrupt lower priority tasks to handle time-critical functions, and asynchronous processing, allowing the computer to manage multiple operations simultaneously, even though it could only execute one instruction at a time. These architectural innovations mattered because of how astronauts would actually use the computer during mission operations. The display and keyboard, known as DSK and pronounced DSKY, provided the human interface to the Apollo guidance computer. It featured a simple numerical display showing 2-digit program numbers, 2-digit verb codes, and 2-digit noun codes, plus 3 5-digit data registers. Astronauts requested actions by entering verb-noun combinations. Verb 16, noun 36 meant display time from ignition. Verb 6, noun 62 meant display surface range and velocity. This seemingly cryptic interface actually represented careful human factors engineering. The limited display forced programmers to design clear, unambiguous interactions, and the numerical codes were faster to enter than text commands while wearing pressurized gloves. Astronauts trained extensively on DSK operations, memorizing the verb-noun combinations for critical mission phases until they became automatic muscle memory. During lunar descent, the commander would monitor Program 63 for braking phase and Program 64 for final approach, while simultaneously flying the lunar module using hand controllers and watching the landing site through the window. The computer wasn't replacing pilot skill, it was amplifying it, handling the calculations and thruster control that would be impossible for a human to perform manually while also navigating and making landing decisions. Soviet designers watched this human-computer integration with profound skepticism. The prevailing view among spacecraft engineers at OKB-1, the design bureau responsible for Soviet crewed spacecraft, was that computers should be ground-based tools that supported mission planning and transmitted guidance commands to spacecraft, where cosmonauts would execute those commands using manual controls. This philosophy reflected both the limitations of Soviet electronics and a cultural preference for human control over automated systems. Vasily Mishin, chief designer of OKB-1 after Sergei Korolev's death in 1966, repeatedly emphasized cosmonaut skill and manual control capability in design reviews for the L-3 lunar landing complex. The LK lunar lander, the Soviet equivalent of the Apollo lunar module, was designed with minimal onboard computation. Cosmonauts would control descent manually using optical sighting through a specialized periscope and hand-operated engine throttles. The spacecraft's onboard computer, the IGLA rendezvous system, could perform basic calculations for orbital mechanics but had no capacity for autonomous navigation or adaptive guidance during descent. This wasn't necessarily an inferior approach for a single landing mission. Soviet test pilots were exceptionally skilled and had demonstrated remarkable ability to land spacecraft manually during the Voskhod and Soyuz programs, but it represented a fundamentally different philosophy about the role of computation in crewed spaceflight. The first direct demonstration of this philosophical difference came during the Apollo 8 mission in December of 1968. Frank Borman, James Lovell, and William Anders became the first humans to leave Earth orbit and travel to another celestial body, a mission profile that required precise navigation across 240,000 miles of space, insertion into lunar orbit, and trans-Earth injection for return. The mission plan called for the Apollo guidance computer to handle all major propulsion burns, with the crew monitoring parameters and ready to take manual control if necessary. Soviet tracking stations, along with facilities in Allied nations, monitored the mission continuously. What they observed was a spacecraft executing complex orbital maneuvers with a precision that suggested real-time adaptive guidance rather than pre-programmed sequences. The lunar orbit insertion burn on December 24 lasted exactly 4 minutes and 7 seconds, reducing the spacecraft's velocity by 2,885 feet per second and placing Apollo 8 into an elliptical lunar orbit with a low point of 70 statute miles. The precision of this burn, executed while the spacecraft was behind the moon with no ground contact possible, demonstrated a level of autonomous computational control Soviet engineers found difficult to accept. The analysis reports prepared after Apollo 8 revealed the intellectual struggle within Soviet technical organizations. Engineers at the Keldij Institute of Applied Mathematics produced calculations showing the computational requirements for real-time lunar orbit insertion, factoring in spacecraft mass, propellant consumption rate, velocity changes, and orbital mechanics. Their conclusion was that such calculations required computational resources far beyond what could fit in a spacecraft-mounted computer, particularly one that also had to handle navigation updates, attitude control, and life support monitoring. The alternative explanation, that American engineers had achieved a level of software optimization and computer architecture efficiency that exceeded Soviet capabilities by an order of magnitude, was professionally difficult to accept. Some analysts suggested that NASA was using coded radio transmissions to secretly provide ground-based guidance updates while claiming autonomous operations for propaganda purposes. This theory persisted despite the obvious problem that such transmissions would be easily detected by Soviet signals intelligence, and no such communications were observed during periods when Apollo 8 was behind the moon and physically unable to receive Earth-based signals. The simpler explanation, that the Apollo guidance computer was performing exactly as NASA described, required acknowledging an uncomfortable technological gap. That gap became undeniable during the Apollo 11 landing sequence on July 20, 1969. At 5 minutes into the powered descent, while the lunar module was still in the automatic guidance phase descending toward the Sea of Tranquility, the display and keyboard showed a program alarm. The code displayed was 1202. Neil Armstrong and Buzz Aldrin had trained on alarm procedures, but this particular code had rarely appeared during simulations. In Houston, flight controller Steve Bales had about 20 seconds to assess the alarm and make a call to either continue or abort the landing. Guidance officer Jack Garman, seated behind Bales, quickly confirmed that 12:02 indicated an executive overflow, meaning the computer was receiving more tasks than it could process in the available time and was shedding lower priority jobs to focus on critical guidance functions. The alarm meant the computer was overloaded, but it was handling the overload correctly by prioritizing descent guidance over less critical displays and housekeeping tasks. Bales called the alarm acceptable, and the landing continued. The 12:02 alarm appeared 4 more times during descent, each time triggering the same rapid assessment and continuation decision. Years later, analysis revealed the overflow was caused by the rendezvous radar, which was left in the wrong configuration and was flooding the computer with unnecessary position data. The fact that the Apollo guidance computer detected this problem shed the unnecessary tasks, maintained control of the descent, and provided clear alarm codes to the crew, and ground controllers demonstrated exactly the kind of robust error handling Margaret Hamilton's team had designed into the software architecture. Soviet engineers listening to the mission audio through ground stations and tracking data understood they were witnessing something unprecedented. A spacecraft computer had encountered an unanticipated failure mode during the most critical phase of the mission and had autonomously resolved the problem without human intervention or ground support, while simultaneously continuing to execute a precision descent to a planetary surface in real time. The complexity of this operational scenario exceeded anything Soviet spacecraft computers had attempted. The closest Soviet equivalent, the Lunar 9 uncrewed soft landing in February of 1966, had executed a pre-programmed descent sequence with no adaptive guidance. If Lunar 9's systems had encountered an unexpected data overflow or computational conflict, the spacecraft would have simply crashed. There was no error detection, no priority scheduling, no ability to shed tasks and maintain critical functions. The design philosophy was different because the computational architecture made real-time adaptive response impossible with available Soviet hardware. Apollo 11 wasn't just demonstrating superior technology, it was demonstrating a different way of thinking about how computers and humans should work together in extreme environments. The landing itself provided additional evidence of computational sophistication. As the lunar module descended below 1,000 feet, Armstrong realized the computer was guiding them toward a crater filled with large boulders, an unsuitable landing site. He switched from automatic to semi-automatic mode, taking manual control of the horizontal velocity, while allowing the computer to continue controlling descent rate and altitude. This mode, Program 66, represented another innovation in human-computer cooperation. Armstrong wasn't fighting the computer or overriding it completely, he was working with it, providing horizontal guidance while the computer handled the complex throttle control and attitude adjustments required to maintain stable descent. The lunar module touched down with about 25 seconds of descent fuel remaining, in a relatively clear area, about 4 miles from the computer's original target. Soviet analysts reviewing the telemetry data focused on those 4 miles of manual correction, initially interpreting it as evidence the computer had failed and required human intervention. They missed the more significant point, which was that the computer had been designed from the beginning to allow exactly this kind of pilot intervention without mode confusion or control conflicts. The Apollo guidance computer treated the astronauts as partners, not passengers. The technical achievement became even more remarkable when examined in detail. During the landing sequence, the Apollo guidance computer was simultaneously running guidance algorithms, calculating the optimal descent trajectory based on current fuel, velocity, and altitude. Navigation programs processing data from the inertial measurement unit and rendezvous radar to update position estimates. Attitude control programs firing 16 reaction control thrusters to maintain proper orientation. Engine control programs adjusting the descent engine throttle in response to guidance commands. Display programs updating the DSKY with current velocity and altitude data, and alarm monitoring programs checking hundreds of system parameters for out-of-tolerance conditions. All of this was happening in a computer with a clock speed of 1.024 MHz and 4 kilobytes of RAM. To put this in perspective, a typical Soviet mainframe of the same era, the BSM-6, had 192 kilobytes of core memory and required a team of operators to manage batch processing of single programs. The Apollo guidance computer was running a true multitasking operating system, managing dozens of concurrent processes, while sitting in a spacecraft bouncing on rocket thrust in 1/6 gravity, operated by astronauts wearing pressure suits. The architectural elegance extended beyond just memory efficiency. Core rope memory, the read-only storage system that held the Apollo guidance computer's software, contained 72 kilobytes of program code and constants, physically woven by workers at the Raytheon plant in Massachusetts. Teams of women, many of whom had previously worked in textile manufacturing, threaded copper wires through or around tiny magnetic cores following detailed programming instructions. Threading a wire through a core represented a binary 1, threading around it represented a 0. This painstaking process, which took weeks to complete for each spacecraft, created a permanent memory that was extraordinarily reliable and radiation-resistant. Each Apollo mission launched with a core rope memory that had been hand-woven months earlier, containing every instruction the computer would execute during the mission. Software updates were impossible once the core rope was manufactured, which meant Hamilton's team had to achieve near-perfect reliability in software that wouldn't be fully tested in operational conditions until astronauts were already committed to the mission. The pressure this created drove the development of formal verification methods, comprehensive simulation, and the systematic testing protocols that would later become standard practice in safety-critical software development across multiple industries. Soviet attempts to understand and replicate this technology revealed the depth of the industrial gap. In 1970, the Ministry of General Machine Building tasked the Scientific Research Institute of Computer Technology with developing an advanced onboard computer for future spacecraft applications. The resulting system, completed in 1973, weighed 190 pounds, consumed 140 watts of power, and had 32 kilobytes of memory. It was a capable computer by Soviet standards, representing genuine advancement in domestic electronics manufacturing, but it was 3 times heavier and consumed 5 times more power than the Apollo guidance computer, while offering similar computational capability. The Institute's engineers understood they had achieved technical parity in basic performance, but had lost the miniaturization and efficiency competition by a substantial margin. More critically, they had no equivalent to the software development methodology and testing infrastructure Hamilton's team had created. Soviet software development for spacecraft remained ad hoc, with individual programmers working on sections of code that were integrated late in development with limited systematic testing. The concept of software engineering as a formal discipline, with defined processes for requirements, design, verification, and quality assurance, had not penetrated Soviet practice. The subsequent Apollo missions provided continuing demonstrations of the guidance computer's reliability and capability. Apollo 12 landed within walking distance of the Surveyor 3 uncrewed probe that had touched down 2 years earlier, a navigation feat requiring precise orbital mechanics calculations and real-time trajectory updates. Apollo 13, following the oxygen tank explosion that crippled the service module, used the lunar module's guidance computer to execute manual burns that returned the spacecraft safely to Earth, with the computer providing navigation data and burn parameters under conditions it was never designed to handle. Apollo 14 upgraded the software to include improved landing site targeting, allowing Alan Shepard to navigate to a more challenging terrain feature. Apollo 15, 16, and 17 carried the most advanced version of the Apollo guidance computer software, with enhanced surface navigation capabilities that allowed astronauts to drive the lunar roving vehicle across miles of lunar terrain, while the computer continuously tracked their position relative to the lunar module. 6 missions, 6 successful landings, 6 perfect returns to Earth, all guided by the same basic computer architecture with cumulative software improvements, but no fundamental hardware changes. The perfect reliability records stood in stark contrast to the Soviet N-1 rocket program, which suffered 4 catastrophic failures between 1969 and 1972. While the N-1's failures stemmed primarily from propulsion and structural issues rather than guidance computers, the program's collapse revealed the systemic problems that had allowed the United States to achieve such dominance in electronics and computational systems. The N-1 suffered from inadequate ground testing, with no test stand capable of firing all 30 first-stage engines simultaneously before flight. It suffered from design instability, with major changes implemented between flight attempts without comprehensive analysis of interactions between systems. Most critically, it suffered from organizational chaos, with competing design bureaus protecting their authority and information rather than cooperating toward mission success. These weren't unique failures of individual engineers, they were systemic characteristics of how the Soviet system organized and executed complex technological programs. The N-1 program spent tremendous resources building flight hardware that exploded on launch pads, while the Apollo guidance computer development spent comparatively modest resources on extensive simulation, software verification, and systematic testing that prevented expensive hardware failures. Vasily Mishin, in technical notes written after his removal as chief designer in 1974, acknowledged that Soviet spacecraft development had prioritized mechanical and propulsion systems while treating electronics and computers as secondary support systems rather than critical mission components. This accurately reflected the material constraints Soviet engineers faced throughout the space race. They could build powerful rockets, innovative propulsion systems, and robust mechanical structures using the industrial capacity and materials science the Soviet economy could support. Advanced electronics required an industrial ecosystem the Soviet Union had never successfully developed, with complex supply chains, competitive component manufacturing, and tight coupling between military aerospace and commercial markets that drove rapid innovation. The Apollo guidance computer succeeded not just because of the brilliance of MIT engineers or Margaret Hamilton's software team, but because it emerged from an industrial system capable of producing millions of reliable integrated circuits, supporting extensive testing and simulation infrastructure, and maintaining dozens of specialized suppliers contributing precision components. The psychological impact on Soviet technical personnel who fully understood what Apollo represented was profound. Yevgeny Rozov, a guidance systems engineer who worked on the L-3 lunar landing complex, recalled in later interviews that the Apollo 11 landing forced a complete reassessment of Soviet approaches to spacecraft automation. The initial dismissiveness, the assumption that American claims were propaganda or that the missions were less autonomous than publicly stated, gave way to careful technical analysis that confirmed everything NASA had described. The Apollo guidance computer had performed exactly as specified, with a level of reliability and sophistication Soviet systems could not match. This realization didn't lead to immediate changes in Soviet spacecraft design. The industrial and organizational constraints remained, but it did create a recognition within technical circles that the United States had achieved systematic advantages in electronics and software that would take decades to overcome. Some engineers began advocating for computer science and software development to be treated as engineering disciplines with the same status as mechanical and electrical engineering, rather than as support functions. These arguments gained limited traction in the 1970s and 80s, but the fundamental problems remained, until the Soviet Union's collapse ended the institutional structures that had created them. The broader implications extended beyond the space race. The Apollo guidance computer demonstrated that properly designed computers could handle mission-critical functions in extreme environments with reliability exceeding mechanical systems. This lesson influenced military aviation, with fly-by-wire control systems becoming standard in advanced fighters by the 1970s. It influenced commercial aviation, with digital flight management systems and autopilots transforming aircraft operations. It influenced nuclear power plant control systems, medical devices, telecommunications infrastructure, and eventually the personal computer revolution. The disciplined engineering methodology Margaret Hamilton's team developed became the foundation for modern safety-critical software development across industries. Every time a fly-by-wire aircraft adjusts control surfaces hundreds of times per second, every time a spacecraft executes an autonomous rendezvous, every time a medical device delivers precise drug dosing, it reflects principles and practices that trace directly back to the constraints and solutions of the Apollo guidance computer program. The Soviet Union eventually developed capable spacecraft computers, with the Argon series in the late 1970s, providing automated rendezvous and docking capability for Soyuz and Progress spacecraft. These systems represented genuine technical achievement and closed some of the gap with American capabilities, but they arrived a decade after Apollo demonstrated what was possible. The Buran space shuttle, which flew one successful automated mission in 1988 before the program's cancellation, used advanced computers that finally matched or exceeded Apollo-era American systems in some respects, but by then the comparison point had shifted to the space shuttle's onboard computers, which operated with megabytes of memory and far greater processing power. The asymmetry remained, with Soviet aerospace computing consistently trailing American developments by 5 to 10 years, just close enough to demonstrate technical competence, but just far enough behind to prevent competitive parity. The 4 kilobytes of RAM that landed men on the moon 6 times represented more than impressive efficiency in computer engineering. It represented a systematic approach to integrating humans and computers in high-stakes environments, treating software as a critical engineering discipline, and building industrial ecosystems capable of producing sophisticated electronics at scale. These were advantages the Soviet system, for all its genuine strengths in theoretical science and heavy engineering, could not overcome. Soviet scientists had not mocked the Apollo computer out of ignorance. They had initially dismissed it based on reasonable assumptions about the relationship between computational resources and mission complexity. When those assumptions proved wrong, when the telemetry data and mission outcomes forced recognition that American engineers had achieved something genuinely revolutionary, the response was not mockery, but a sobering realization of how far the technological gap extended. The computer that seemed impossibly limited by Soviet standards had proven more capable than systems orders of magnitude larger, because capability derived not just from hardware resources but from architecture, software, and systematic engineering excellence. If you found this exploration of Cold War technological competition valuable, subscribe to see more documentaries examining the engineering innovations and strategic decisions that shaped this era. Each video provides detailed analysis of real events, verifiable technical facts, and the human stories behind historical turning points. Subscribe now to continue learning about the technology and people who defined the Cold War.